All right. Hello, everyone. My name is Andre, and along with Ellie, Richard, Danny, and Vivian, we are Team Sterilization and Brochollini. The prompt that we chose to work on for the past 2 days was inline UV sterilization. So our team aimed to design a device that uses UV radiation to sterilize the air in a ventilator patient's exhalation tube. The task at hand was to take the air from the patient and make sure that this air is sterilized from any contaminants, to make sure that the air is safe for once it is excreted. We also had to take into consideration safety. We didn't want the dangerous UVC radiation to be harming the patient or the personnel that might be around the person. So from our research, we concluded that using UVC light would be our best solution to be able to sterilize viruses. And from this, our next question kind of was, how do we ensure that all of the exhaled air has received sufficient UV exposure? And to find the answer to that, we had a mathematical calculation model that we made. So assuming that the average human has around 6 liters per minute of ventilation, and knowing that from the prompt that the standard cross-sectional area of a tube has a 20 millimeter diameter, we were able to calculate the speed of air through the tube. And combining this with our research, which said that at 2 centimeters from the UV source, which is what we would have inside our tube, you would only need around half a second to ensure 99.9% sterilization. So to inform our prototyping process, we use this as kind of finding out how long would this device have to be attached to the tubes in order to ensure full sterilization. As far as physical prototyping goes, we kind of worked with what we had. So we took a ventilator mask, which normally has 2 separate ports. It has one for inhalation and one for exhalation. And the one we want to work on is the exhalation line, which is a standard 22 millimeters. And then our device consisted of a black UV resistant tube that has UV LEDs inside. And this device has been made so that the entire length of it is more than 13 centimeters in order to allow for that half a second of contact for all the air that is exhaled by the patient. This is kind of the side view. You can see inside we have an array of LEDs that would be able to provide sufficient power that they are able to sterilize the inside. And the black tubing that we're using ensures that there's no harmful radiation that is able to go outside and harm the patient or maybe the medical personnel that's there in the room with them. Other safety precautions that we also took were using a one-way valve at kind of the entry to our device to ensure the directionality of airflow and ensure that once this air has been sterilized, it can't go back to the patient and harm them. And also we paid extreme attention to make sure that there's no radiation that can kind of go out of the tube and harm those around them. And from an electrical perspective, we also wanted to make sure that failure of one of the LEDs inside doesn't cause failure of the entire device. So we coupled all the things in parallel and connect them to a 9-volt battery to ensure that this device is portable and is also able to function even if some components might fail. So this is our final prototype. This is what it looks like. Based on our calculations, we were not able to do real testing on its sterilization efficiency, but based on our calculations, with it being at least 13 centimeters long, it should be able to achieve at least 99.9% efficacy of sterilization of viral particles for the exhaled air from the patient. Thank you, and I would like to open the floor to questions now.